Welcome back to Python DSA. In this video, we're doing a complete deep dive into strings, the universal text type in Python. Strings are more than just characters in quotes. They're an immutable data structure with a rich set of algorithms built around them, and they appear in virtually every Python program you'll ever write. We'll go from memory internals all the way to KMP search and sliding window algorithms. Let's get into it. A string in Python is an immutable sequence of Unicode characters. It's the foundational text type. Everything from a single letter to a multi-megabyte document is a str. Click under the hood. Each character is a Unicode code point, a number that uniquely identifies a character in the Unicode standard. Python 3 uses a flexible internal representation defined in PEP 393, which chooses the smallest possible fixed width encoding based on the widest character in the string. 1 byte per character for pure ASCII, 2 for Latin extended, 4 for full Unicode including emoji. More on that in the next slide. Click why do we call a string a data structure? Because it has all the properties of 1. Random access by index in O1. Slicing, iteration, and membership support. Built-in algorithms for search, split, and replace. And it's the foundation for text processing, parsing, and pattern matching. It's not just a primitive, it's a fully equipped sequence type. Click the code confirms it. Lens runs in O1, because the length is stored in the object header. 0 is O1, direct access. -1 uses negative indexing from the end. Click the diagram shows both positive and negative index mappings for hello. Index 0 through 4 run forward. Index -5 through -1 run backward, meeting the same characters. 2 views, same string, O1, access from either end. Let's look inside a Python string object to understand its memory behavior. This matters when you're working with large text or mixed language content. PEP 393 defines 3 internal representations. If every character has a code point, at or below U plus 007F, pure ASCII, Python stores 1 byte per character. That's the most compact and most common case. If any character goes up to U plus FFFF Latin extended, Greek, CJK Python, upgrades to 2 bytes per character for the entire string. If any character requires more than that, including emoji, it's 4 bytes per character throughout. Click the size measurements make this concrete. Hello, 5 ASCII characters, takes 54 bytes total. That's 49 bytes of object overhead, plus 5 bytes of data. Add an accented E, and the whole string jumps to 78 bytes, because the entire internal buffer widens to 2 bytes per character. Add an emoji, 120 bytes, 4 bytes per character, including the ASCII ones. The widest character dictates the encoding for the whole string. Keep this in mind when you're building strings that mix plain ASCII with occasional Unicode characters. Click string interning is Python's optimization for short, identifier-like strings. Python caches them and reuses the same object in memory. Hello assigned to 2 different variables ends up being the same object. A is B is true. But hello world with a space is not interned. It gets 2 separate objects, so is returns false. == for value equality will always work. Is for identity should never be used for string comparison unless you understand interning deeply. Click is the most important practical consequence of immutability. Every time you modify a string with +=, you're not modifying anything, you're allocating a brand new string object. In a loop that does 1,000 concatenations, you're creating 1,000 objects, each copying all previous content. O(n)² total. Use join list instead. We'll see this in detail later. Python gives you many ways to create strings. Let's cover them all. Click 4 literal forms. Single quotes, double quotes, triple single, triple double. Single and double are equivalent. Use whichever avoids escaping inside the string. Triple quoted strings span multiple lines and preserve all white space and new lines literally. Click raw strings prefixed with R. Disable all escape sequence processing. Backslashes are treated as literal backslashes. This is essential for Windows file paths and for regular expressions, where backslashes have special meaning. RD+ is a regex digit pattern. Without the R prefix, you'd have to write D+. Byte strings, B, produce a bytes object, not a str. Each element is an integer 0 to 255, not a character. We'll cover the str/bytes relationship in a dedicated slide. Click F strings are the modern, recommended way to interpolate values into strings. Whatever you put inside the curly braces is a live Python expression, variables, arithmetic, method calls, format specifiers. The .1f format spec says, float with 1 decimal place. The equals suffix in debug expressions prints both the expression and its value, invaluable during debugging. Alignment and padding are built in, with greater than, less than, and caret. Click str.format is the predecessor, still perfectly valid, especially for more complex positional and keyword substitution patterns. Percent formatting is the legacy approach, still works, but avoided in new code. String multiplication repeats, *40 gives you 40 dashes, and ord/chr convert between characters and their Unicode code points. Next, indexing and slicing are arguably the most used string operations, and they deserve more attention than they usually get. Click indexing is 01. 0 is the first character, -1 is the last. Negative indices count backward from the end. -6 is the same character as 7 in our 13-character string. Click slicing uses the form start, stop, step. The stop is exclusive, so 0 to 5 gives you characters at indices 0, 1, 2, 3, 4. All three parts are optional. Omitting start means from the beginning. Omitting stop means to the end. Omitting step means step of 1 is a shallow copy of the entire string. The step parameter is powerful. 2 takes every other character. And -1, step of -1, reverses the entire string. That's the idiomatic Python string reversal, one expression, on. Click the diagrams make slicing visual. Zone to 4 highlights indices 1, 2, 3. Those three characters become the new string. -1 steps backward through every character, producing the full reverse. Click complexity table. Index is 01. Slice of length k is OK. It must copy those k characters into a new object. Full reverse is on. Lens is 01, stored in the header. Substring membership sub in s is on times m. Worst case, it has to scan for the pattern. And a critical point. The original string is never modified. Slicing always returns a new string object. The source is unchanged. Next. Python strings come with a rich standard library of built-in methods. Let's break them into categories. Click case and whitespace, upper, lower, title, swap case, capitalize. All return new strings with case transformations applied, because strings are immutable. Strip removes leading and trailing whitespace. Lstrip and rstrip strip one side only. You can pass a string of characters to strip those specific characters instead of whitespace. Search and test, find, returns the index of the first occurrence, or -1 if not found. Index does the same, but raises value error on failure. Use find when absence is a valid outcome, index when it's an error. Rfind searches from the right. Count returns the number of non-overlapping occurrences. Starts with and ends with test prefixes and suffixes. These predicates, isalpha, isdigit, isalnum, test character composition. Click split, join, and replace. Split divides on a delimiter, returning a list. Split lines handles any line-ending convention. The max split argument caps how many splits are performed, useful when you only need the first few parts. Join is the inverse of split and is the correct way to concatenate many strings. The separator string goes on the left, the list of parts on the right. Join words with an empty separator concatenates with no separator at all. Replace substitutes all occurrences by default. Pass a count to limit replacements. Partition splits on the first occurrence of a separator and always returns exactly a 3-tuple, the part before, the separator, and the part after. It's cleaner than split when you expect exactly one separator. Next, let's go deep on string formatting. F-strings have a surprisingly rich format specification language that most people only scratch the surface of. Click Format Specifiers, live inside the curly braces after a colon. Point 2F adds a comma separator and 2 decimal places. E switches to scientific notation. Greater than, less than. Caret control alignment, right, left, center, with an optional width. For integers, B gives binary. #010b adds the 0b prefix and pads to width 10 with zeros. #x gives lowercase hex. Click the x equals debug syntax, introduced in Python 3.8, prints both the expression text and its value x equals 10. 3 keystrokes instead of writing fx equals x. Use it constantly while debugging. Nested f-strings let you compute the format specifier dynamically. FPI width precision f uses variables for both width and precision. The inner braces are evaluated first. Click str.format, supports positional references, 0 and 1, and back to 0 again, and keyword references. The conversion flags more mess and it's n. Apply repr, str, and ASCII to the value before formatting. Click string.template is the safe alternative for user-facing substitution. It uses $ syntax instead of curly braces, and crucially, it never executes arbitrary code. Safe_substitute leaves unknown placeholders intact, rather than raising an exception. Textwrap.wrap and textwrap.dedent round out the toolkit for handling long text and indented multiline strings cleanly. Next, strings implement Python's full sequence protocol. Every operation that works on a list or tuple works on a string, with the restriction that strings are read-only. Click Iteration with for CH and S, traverses every character, ON. Enumerates, gives you both the index and the character, simultaneously. Combining iteration with iSupper lets you find all uppercase characters and their positions in one clean loop. Click Membership Testing with IN, does a substring search, ON, for a single character, ON times M, for a multi-character pattern. Zip AB, pairs up characters from two strings for parallel processing. Sorteds returns a sorted list of the individual characters, combine with join to get a sorted string back. Filter and map work directly on string characters, since they're iterable. List comprehension over a string with a condition is the most Pythonic approach for extracting characters that match a predicate. Click the sequence operations table is your reference. O1 for index and length, ONK for slices of length K, ON for membership, iteration, min, max, ON log n for sorted. String concatenation with plus is ON plus M. It must allocate a new string of the combined size. Click the warning and code example here, are essential. The plus equals in a loop pattern is the most common Python string performance mistake. Each iteration allocates a new string object and copies all previous content into it. One character per iteration in the worst case gives you ON squared total. The join pattern collects all parts in a list, O1 appends, then does a single ON join at the end. Always use join for incremental string construction. Regular expressions regex are the power tool for string pattern matching, extraction, and transformation. Python's re module provides full, Perl-compatible regex support. Click 4 core functions. Re.search finds the first match anywhere in the string and returns a match object, or none. Re.findAll returns a list of all non-overlapping match strings. Re.match only matches at the start of the string. If the pattern doesn't match from position 0, it returns none. And re.sub replaces all matches with a replacement string. Click groups let you extract parts of a match. Wrap a sub-pattern in parentheses to create a capture group. M.group1 gets the first group. M.groups gets all groups as a tuple. Named groups with p less than name greater than let you access captures by name mgroup user, which makes complex patterns much more readable. Click re.compile, pre-compiles a pattern into a regex object. The compiled object has the same methods, findAll, search, sub, but the expensive compilation step only happens once. Always compile patterns that appear inside loops or are reused across function calls. Re.split, with a regex delimiter, can tokenize on complex patterns, multiple spaces, mixed punctuation, any combination you can express as a regex. Click the metacharacter cheat sheet on the right, is your reference. Dot matches any non-new line. D is digits, W is word characters, S is whitespace, caret anchors to the start, dollar to the end. Asterisk plus, and, are quantifiers. M(n) specifies repetition ranges. Capture groups with parentheses, alternation with pipe, look ahead with, equals. Click the 4 common flags. Re-I for case-insensitive matching. Re-M makes caret and dollar match at line boundaries. Re-S makes dot match new lines too, and Re.X allows whitespace and comments inside patterns for readability. Next, let's look under the hood of substring search, from the naive approach to the linear time algorithms used in production. Click Naive Search is ON times M. For each of the n-m plus 1 possible starting positions in the text, we check whether the next m characters match the pattern. Python's built-in in operator and str.find use a variant of this. Worst case AAA, searching for AAA-AB, the pathological case, triggers full ONM behavior. For most practical inputs it's much faster. Click KMP, Knuth Morris Pratt achieves ON plus M by never re-examining text characters. The key idea is the LPS table longest proper prefix, which is also a suffix. When a mismatch occurs at position J in the pattern, instead of resetting J to 0, we reset it to LPS to 1, the length of the longest valid border of the pattern up to that point. This means we skip ahead without backtracking in the text. The LPS table is built in OM as a pre-processing step. The main scan is ON, total, ON plus M. Click Rabin-Karp uses a rolling hash. Compute the hash of the pattern, and the hash of the first m characters of text. Then slide a window of size m across the text, updating the hash in O1 by subtracting the outgoing character and adding the incoming one. Hash match means possible match, verify character by character. Hash mismatch means skip, average ON plus M, and the rolling hash update is the clever part. Click the algorithm comparison table. Naive is ONM time, but O1, space, the simplest. KMP is ON plus M, time and OM space for the LPS table. Rabin-Karp is ON plus M, average and O1 space, but degrades to ONM under hash collision. Python's built-in is naive in the worst case. For production string search on large text, KMP or Boyer-Moore are the go-to choices. Next, Let's work through the classic string algorithm problems you'll encounter in interviews. Click palindrome check with 2 pointers. Normalize by lowercasing and removing spaces. Then use 2 pointers starting from each end. Advance them toward the center, and if any pair of characters doesn't match, return false. If the pointers cross, return true. ON time, O1 space. Longest palindromic substring uses the expand around center approach. For each position in the string, we try to expand outward, as long as the characters on both sides match. We check both odd length centers, centered at one character, and even length centers, centered between 2 characters. The longest result across all expansions is the answer. ON squared, time, O1 space. Optimal for interview contexts. Click anagram check using counter. 2 strings are anagrams if and only if they have identical character frequencies. Counters equals counter T does exactly that check in ON. If the lengths differ, return false immediately as an early exit. The check itself is ON either way. Click Group Anagrams from a list of words. The key insight: all anagrams of a word sort to the same string. So we use tuple, sorted W, as a dictionary key and group words that share the same key. ON times K log K, where N is the number of words, and K is the average word length. The callout notes that for maximum performance, you can use a frequency tuple of 26 integers as the key, instead of sorting OK per word, instead of OK log K. 2 of the most important algorithmic patterns for string problems: the sliding window and 2 pointers. Click longest substring without repeating characters is the prototypical sliding window problem. We maintain a window defined by left and right pointers and a dictionary mapping each character to its last seen index. As we advance right, if the current character was seen within the current window, meaning its last index is at or after left, we shrink the window by advancing left past that previous occurrence. Update the last seen index, update the max length. ON. Each character is processed at most twice. The 3 examples: ABC, ABCBB, right pointing arrow 3, ABC, BBBBB, right pointing arrow 1B, PWWKEW, right pointing arrow 3, WKE. The key is the condition char underscore IDX, CHCH greater than equals left. Without it, we'd shrink the window based on stale index information from before the current window started. Click minimum window substring is the harder sliding window. We need the smallest window in string S that contains all characters of string T. We track a need counter and a missing count. Expand right, crossing off characters we need from missing. When missing reaches 0, we have a valid window. Record it and shrink from the left while validity holds. Each shrink potentially invalidates the window, incrementing missing again and resuming expansion. ON. Again, each character visited at most twice. Click the diagram visualizes the window state for ABC, ABC, BB. The green highlighted portion is the current valid window, 3 characters wide. As the window slides right, it grows and shrinks based on the repeat check. Click valid palindrome 2, with at most 1 deletion, shows the 2-pointer approach. Walk from both ends. On a mismatch, we have 1 deletion to spend. Try skipping the left character and check if the remainder is a palindrome. Or try skipping the right character and check the same. If either works, return true. ON. Next. More classic interview patterns: string manipulation and transformation. Click reverse words in a sentence. Join split -1. In one line, split on any whitespace, reverse the list, rejoin. Split, without an argument, handles multiple consecutive spaces. The manual version, without using split, scans character by character to collect word characters, appending completed words to a list, then joins in reverse. ON. Click run length encoding string compression. Scan for runs of identical characters. For each run, append the character and its count if greater than 1. Return the compressed version only if it's actually shorter than the original. AABCCCDDDD becomes a 2BC3D4. ON. Click decode string handles nested encoded strings, like 3-2. This is a stack problem. As we scan, digits accumulate into cur_num. An opening bracket pushes the current string and current number onto the stack and resets both. A closing bracket pops the previous string and repeat count, rebuilding cur_str equals previous_str plus cur_str *num. Regular characters append to cur_str. After 1 scan left to right, 3-2 becomes a babab. ON. Click Roman numerals. Int underscore to underscore Roman greedily subtracts the largest denominations, appending their symbols. The values list includes the subtraction cases: 900 before 1000, 400 before 500, and so on. Roman underscore to underscore int scans left to right. If the current symbol's value is less than the next symbol's value, it represents a subtraction, so we subtract. Otherwise we add. MCMXCIV, right pointing arrow 1994. Python has three closely related binary and text types, and understanding when to use each prevents a class of bugs that can be very hard to diagnose. Click str is immutable Unicode text. Len, hello globe, is 8 code points, including the emoji is 1 character. It's what you use for all text operations. Bytes is an immutable sequence of integers in the range 0 to 255. You get bytes from encoding a string. Hello globe.encode, UTF-8, produces 11 bytes because the emoji takes 4 bytes in UTF-8. Indexing a bytes object returns an integer, not a character. Slicing returns another bytes object. Click byte array is the mutable version of bytes. You can change individual bytes in place. Base 0 equals 104 changes the first byte from 72 capital H to 104 lowercase h. Append and extend. Add bytes. This is the type you use for in-place binary manipulation. Memory view provides a zero-copy view into binary data. Slicing a memory view doesn't copy the underlying bytes. You're just creating a view over a different region. MV0 equals 104 mutates the original byte array through the view. Essential for high-performance binary protocols. Click. The flow diagram summarizes the relationships. str encode ENC converts to bytes. Bytes.decode ENC converts back. Byte array bytes makes bytes mutable. Bytes byte array freezes them again. Click the comparison table. str and bytes are immutable. Byte array is mutable. The unit for str is a code point. For the binary types, it's a byte as an integer. Use str for text, bytes for network data, file I/O, and cryptographic operations. Byte array when you need in-place binary mutation. Click the callout. Always specify encoding explicitly. Never rely on the platform default. Use UTF-8 for anything that crosses system boundaries. Next, we've said that plus equals in a loop is on squared. This slide makes that concrete and shows the alternatives. Click build_bad does exactly what you should never do. Concatenate onto a result string in a loop. Each plus equals allocates a new string object, copies all previous content, and appends the new piece. Total work: 1 copy plus 2 copies plus 3 copies. Triangular number on squared. Build_join is the fix. Collect pieces in a list with O1, appends, then do a single .join call that allocates exactly one string of the right size and fills it in. On. Build_sio uses IO string IO, a file-like object backed by a string buffer. Write to it like a file, then call getValue to get the final string. Also on, and useful when you need a file-like interface. Click. IO string IO shines in a specific scenario, feeding a string to code that expects a file object. The CSV.reader example is perfect. It expects a file handle, but we have a CSV string in memory. Wrap it in string IO, and it just works. No temp file needed. Click the bar chart makes the quadratic versus linear difference visceral. At n equals 100,000 characters, plus equals takes around 65 milliseconds. Join takes around 8. At n equals 1 million, plus equals would take several seconds. Join would take 100 milliseconds. The gap only grows. Click the bonus snippet shows how to capture print output into a string by temporarily redirecting sysstd out to a string IO buffer. This is the standard Python technique for capturing output from code you can't modify. Next, 3 standard library modules that every Python programmer should have at their fingertips for string work. Click collections.counter is a frequency map with superpowers. Feed it a string and it counts every character. Most_common 3 returns the top 3 by frequency. Counter arithmetic works exactly as you'd expect. Subtract one counter from another and get the difference. Essential for anagram problems, character frequency questions, and text analysis. Click the string module provides pre-built character set constants as strings. String.ASCII_lowercase, string.digits, string.punctuation, string.printable. All available as plain strings you can iterate, join, or convert to sets. Converting to a set gives you O1 membership testing instead of ON, which matters when you're checking millions of characters. Click Unicode data gives you programmatic access to every character's Unicode properties. Unicode data.name returns Latin capital letter A. Unicode data.category returns the Unicode category code LU for uppercase letter Z's for space separator. Normalization with NFC and NFD is critical when comparing strings that might represent the same character in different ways. For example, the letter E can be stored as a single composed code point or as the base E plus a combining accent mark. Without normalization, those two representations compare as unequal even though they look identical. strsashi, added in Python 3.7, lets you fast-path ASCII-only strings before doing heavier Unicode processing. Click difflib.sequencematcher computes a similarity ratio between two strings. Get underscore close underscore matches finds the closest match from a list of candidates, useful for spell checking, command line argument suggestions, or fuzzy search. End-if produces a human-readable diff of 2 string lists. Ext. Full complexity reference. Print this and keep it close. Click core string operations. Index and length are O1. Slice of length k is O(k). Concatenation with plus is ON plus M. Membership with in for a single character is ON. For a substring, it's ON times M worst case. Find, replace, split, join, lower, upper, strip, all ON. Equality comparison is O, min, n, bo, vim. It short circuits on the first mismatch. The immutability cost table restates the critical rule. Plus equals in a loop is ON squared. Join and string IO are ON. There's no in between. If you're building strings incrementally, choose one of the ON approaches. Click searching algorithms. Naive and Python's in are ONM worst case. KMP and Rabin-Karp are ON plus M. Boyer-Moore has an ON per meter best case, faster than linear on long patterns, making it the choice for production full-text search engines. Click memory. Object overhead is about 49 bytes. ASCII strings are 1 byte per character above that. Once you introduce any character above U plus 007F, the entire string widens to 2 or 4 bytes per character. This is why mixing ASCII and emoji in a long string significantly increases memory usage. Click regex. Compilation is OM, the pattern length. Compiled search is ON to ONM, depending on the pattern. This is why you compile once and reuse. Pay the compilation cost once. Amortize it across all searches. Next, let's consolidate the most common mistakes and their corresponding fixes. Click pitfall 1, string plus equals in a loop. We've said it 3 times now. It's ON squared. Use join, pitfall 2. Using equals equals to test for none. It works, but the Pythonic idiom is none, and is not none. None is a singleton. Identity comparison is both correct and faster. Pitfall 3, attempting 0 equals h on a string. This raises type error immediately. Strings are immutable. If you need character level mutation, work with a list of characters and join at the end. Pitfall 4, using is to compare string values. A is B, tests object identity, not equality. Intern strings make this true sometimes, but it breaks for non-intern strings. Always use equals equals for string equality. Pitfall 5, forgetting strip before comparison. User input almost always has leading or trailing whitespace. Yes equals equals yes is false. Always strip before comparing user-provided strings. Pitfall 6, calling re.findAll, pattern. Inside a loop, without compiling. Every call recompiles the pattern. Compile once outside the loop. Reuse the compiled object. Pitfall 7, decoding bytes with the wrong encoding. bxff.decode, UTF-8, raises Unicode decode error. Know your encoding. Click best practices. Join for concatenation. F-strings for formatting. str-translate, with maketrans for bulk character removal or replacement. It's significantly faster than calling replace in a loop, because it processes the entire string in one C-level pass. Compile regex patterns. Call isashii before expensive Unicode normalization. Always specify encoding when opening files. Partition instead of split when you're splitting on the first occurrence only. And hashlib for secure operations involving passwords or sensitive strings. Never use plain string equality for security critical comparisons. Let's bring it all together. Click the type hierarchy diagram. Text processing splits into str for Unicode text and bytes for binary. Bytes upgrades to byte array for mutability. str branches into IO string IO for file-like buffering, re for pattern matching, and string.template for safe substitution. Know which tool each branch is for. Click the when to use what table at left is your decision guide. F-strings for formatting. Join for building large strings. re.compile for pattern matching. Counters for frequency analysis. IO string IO for file-like string interfaces. Bytes and byte array for binary data. String.template for user-facing safe substitution. difflib for similarity and fuzzy matching. Click the quick API reference at right is pure reference code. Case methods, test predicates, search methods, transform methods, slice syntax, format specifiers, and encode/decode, all in one block. Screenshot it. Click last word. Strings are in every Python program. str.join over plus equals, f-strings over %, and .format in new code. re.compile, over repeated re.search. Counter over manual frequency dicks. These 4 habits alone will make your string code measurably faster and more readable. And that's a wrap on Python strings. We went from Unicode internals and PEP 393 memory layout through slicing, every major method, F-string format specifiers, regex, KMP and Rabin-Karp search, palindromes, anagrams, sliding window patterns, string manipulation, str versus bytes, string IO, and the collections and string module utilities. If this was helpful, hit the like button and subscribe to stay current with the Python DSA series. Drop any questions in the comments and I'll get back to you. See you in the next one.